Space begins above us as a quiet field of stars, with long shadows between faint clouds and distant arcs of light. In that calm, we'll meet extreme objects, black holes we can weigh, neutron stars we can time, quark stars we still debate, and a proposed cousin, the Gravastar, a dark twin that could sit where a black hole seems to be. We'll unpack the needed physics in plain words: vacuum energy, quantum degeneracy pressure, and the curvature of space-time. Then we'll widen the view to dark matter, dark energy, the Big Bang, and possible endings for the universe, before closing with a simple reflection on what science is and why curiosity endures. If this slow tour suits you, please like and subscribe. Quiet support matters. Let's begin. When you look up at a clear night sky, it feels calm. Stars flicker, soft lanes of light drift, and the darkness between them seems quiet. That quiet is only from far away, across space or regions where matter and energy reach states our senses never meet. Some are well-known black holes and neutron stars. Others remain ideas under study, like quark stars. And there is a third path some scientists propose for the fate of very massive stars, a path that could hide beside black holes and look much the same. It's called a Gravastar. To reach it, begin with a basic question. What becomes of a massive star when its fuel runs out? A star shines because nuclear fusion in its core pushes outward, balancing gravity that pulls inward. When the fuel fades, the push weakens. Gravity no longer has a full counterforce. The core starts to fall in on itself. In a star many times heavier than our sun, that collapse happens in less than a second. The outer layers rush inward, strike the core, and rebound. The shock tears through the star and blows the surface into space. This is a supernova. For a short time, it outshines a whole galaxy. It leaves behind a compact remnant. Most people learn two standard outcomes. If the star's core is heavy but not extreme, the collapse stops when neutrons, the particles inside atomic nuclei, are packed as tightly as physics allows. The result is a neutron star. It is only about 12 miles across, yet heavier than our Sunday. If the core is even heavier, its own gravity keeps squeezing. The standard picture says it shrinks without limit, reaching a point with no size and near infinite density called a singularity. Around that point forms an event horizon, a boundary in space-time. Cross it, and nothing, not even light, can get out again. That is a black hole. The black hole picture works well for many observations, yet the singularity at the center is a warning sign in our math. A singularity says our current laws have been pushed past the range where they make sense. Equations spit out infinities. We can still predict what an outside observer would see, but we do not have a clean description of the inside. For many physicists, this is not satisfying. They expect that a better theory, one that includes both gravity and quantum physics in full, will remove the singularity and replace it with something understandable. One proposal along those lines is the Gravastar, short for gravitational vacuum star. It was put forward in the early 2000s as an alternative end state for core collapse. The idea keeps the strong gravity and the compact size. It changes what forms at the center. Instead of shrinking to a point, the collapsing matter undergoes a phase change. A phase change is a shift in how matter is arranged. Water freezing into ice or boiling into steam are common examples. Carbon turning into diamond under high pressure is another. In the Gravastar idea, the phase change is far more exotic. The interior turns into a kind of vacuum energy. Vacuum energy needs a careful plain explanation. In quantum physics, what we call empty space is not truly empty. Fields fill space, and even when there are no particles present, those fields have a small, constant energy. This is vacuum energy. It does not vanish. In most places, it is spread out and weak. During a violent collapse, though, conditions may force matter to convert into a region dominated by this vacuum energy. You can picture the difference by thinking of a sponge full of water. When the sponge is wide, the water is spread across it. If you could squeeze the sponge to a tiny size without losing any water, the water would be very concentrated. In a gravastar, the water in that picture is the vacuum energy. It becomes dense, not infinite, but extremely high. This concentration matters because vacuum energy has an unusual effect on gravity. Most matter pulls together. Vacuum energy pushes outward. In Einstein's theory, this kind of energy acts like a negative pressure. It stretches space. On the largest scales, something like it may be linked to dark energy, which drives the expansion of the universe to speed up. Inside a gravastar, the outward push from this dense vacuum energy can meet the inward pull from the object's gravity. The two effects can balance. Collapse slows and stops before a singularity forms. The interior becomes a stable, expanding like core held in place by the very gravity that tried to crush it. The picture does not end with a simple core. The Gravastar model also includes a thin shell around that interior. This shell is made of exotic matter. Exotic here means matter in a state not found in normal stars or planets. One candidate state is a Bose-Einstein condensate. In that state, many particles act as one, sharing the same quantum wave. It usually forms at temperatures near absolute zero, where motion almost stops. In the Gravastar idea, the shell would be extremely cold, only a tiny fraction of a degree above absolute zero, and under huge tension. Think of a drum skin pulled tight across a frame, but on a scale where the skin might be thinner than an atom, and the energy it holds back is enormous. The job of this shell is to separate two very different regions. Inside is the dense vacuum energy that pushes outward. Outside is normal space where gravity behaves as we expect. The shell keeps the core from expanding into the outside world. It also provides the place where infalling matter ends its journey. In the black hole picture, matter that falls in goes past the event horizon and is lost to the outside forever. In the Gravastar picture, there is no true horizon. Instead, infalling matter piles up on the shell or interacts with it. From far away, the difference is not easy to see because gravity near the object is strong either way. So what would such an object look like if we observed it with telescopes? In most ways, it would mimic a black hole. Light passing nearby would bend. Time near it would slow compared to time far away. If gas falls toward it, that gas would form a hot, bright disk. Friction and magnetic fields in the disk would heat the gas to high temperatures and make it shine in X-rays and other high-energy light. The inner part of the disk would appear to vanish at a certain radius, just as it does around a black hole, because the gas either falls in or strikes a boundary and loses energy in a way we cannot see directly. The silhouette against a glowing background could show a shadow, much like the images from the Event Horizon Telescope, which photographed the regions around the supermassive objects in M87 and our own galaxy's center. With present tools, a gravastar might be indistinguishable from a black hole. Yet, within the theory, there is one key distinction. A classic black hole has an event horizon. The event horizon is not a physical surface. It is a boundary in space-time that marks the limit of escape. Signals from inside can never reach the outside. Cross it, and every future path leads inward to the central region. In the standard picture, that path ends at the singularity where our equations break. This is the part many physicists want to replace with a better description. A gravastar removes the singularity by replacing the inner region with vacuum energy and a thin shell. Without a singularity, there is also no strict event horizon in the mathematical sense. Instead, there is a surface extremely close to where the horizon would be for a black hole of the same mass, where matter and light meet the shell. Because gravity there is so strong, anything that reaches the shell is redshifted, meaning its light is stretched to longer wavelengths and lowered in energy. From far away, this makes the object look almost perfectly black. Light struggles to get out. The time it takes for signals to return can be so long that, for practical observing, it might as well be never. This is why separating the two ideas with current data is hard. To understand why neutron stars stop their collapse but heavier cores might not, it helps to recall what holds a neutron star up. Inside, particles obey quantum rules. One of those rules says that identical particles do not like to share the same state. This creates a pressure called degeneracy pressure. Electrons provided in white dwarfs, neutrons provided in neutron stars. Degeneracy pressure does not depend on heat. It comes from the basic quantum nature of matter. In neutron stars, this pressure plus nuclear forces can balance gravity up to a limit. Beyond that limit, called the Tolman-Oppenheimer-Volkoff limit, gravity wins. The Gravastar idea says that at this point, instead of forming a singularity, matter transitions into vacuum energy and forms the shell core structure. The math behind these models uses general relativity, which describes how mass and energy curve space-time, and quantum theory, which describes matter on very small scales. These two frameworks are both well tested on their own, but they do not yet merge into a single, complete theory. That gap leaves room for proposals like Gravastars. They are not claims of discovery. They are ideas designed to see if there are logical, stable solutions that look like black holes from the outside, yet avoid the singularity inside. Researchers then ask, would such objects be stable over time? Would they form naturally in supernovae? What signals would give them away? One possible difference lies in how the surface would behave. If there is a shell, infalling matter could strike it and release energy. A small portion might leak back out as a faint, delayed flash. In practice, the extreme redshift near the surface would stretch and dim that light until it blends into the background, making it hard to detect. Another clue is how the object rings after a disturbance. When two black holes merge, the remnant settles with a well-predicted gravitational wave ringdown. If a surface replaces a true horizon, weak, late-time echoes could appear as waves bounce and return. Teams are searching detector data for such signatures, but results so far are not decisive. A gravastar, by contrast, would not be all boundary and no surface. It would have an actual skin, an ultra-thin shell of exotic matter. Exotic is the right word, yet it is still matter, not a purely mathematical edge. That small-sounding difference changes how the object handles light, heat, and information. A surface can absorb, reflect, or slowly release energy, while a horizon, in the usual sense, is only a one-way limit. This brings us to the information paradox, a long-standing puzzle in black hole physics. The question seems simple. What happens to information about the things that fall in? In quantum mechanics, information is never destroyed. If you know the full quantum state of a system now, the rules say you can, in principle, work out its past and future. But the classic black hole picture says anything crossing the event horizon is gone to the outside world forever. You could throw in a book, an atom, or a star, and from the outside you would never recover the details of what went in. The laws of quantum mechanics don't accept that. The conflict between no loss and no escape is the paradox. Many ideas try to resolve its subtle correlations in the radiation, holography, quantum hair, but the debate remains active. A Gravastar avoids the sharpest edge of this conflict because it has no event horizon and no singularity. When matter and light meet the shell, they do not vanish into a region from which signals can never return. Instead, the shell and the interior can, at least in principle, store and process the information. It could be encoded in the shell's quantum state or in the structure of the vacuum energy inside. Extreme redshift would make any outgoing signal slow and faint, perhaps too faint for any detector we have, yet not fundamentally impossible. In that way, the model sidesteps the paradox rather than solving it inside a black hole. The next question is practical. Do gravastars exist in nature, or are they only neat solutions on paper? The honest answer is that we do not know. No telescope has confirmed a gravastar. It is possible the universe prefers the standard path and makes only black holes and neutron stars. Still, a model that is consistent with general relativity and basic quantum ideas is worth study. The hard part is that, from far away, a gravastar would look almost exactly like a black hole of the same mass and spin. Both would bend light the same way. Both would anchor hot disks that glow in X-rays. Both would cast a dark silhouette against surrounding light. To tell them apart, we need to hunt for very small differences. Gravitational waves offer one path. These are tiny ripples in space-time, created when massive objects move and change shape. When two black holes merge, the new object settles down by ringing, much like a bell, with a pattern of waves called a ring down. The shape and timing of that ring down are predicted by Einstein's equations for a horizon-covered object. If, instead, two gravastars merge, there would be a difference near the end of the signal, because gravastars have surfaces. Some of the waves could reflect off those surfaces and return after a short delay, creating weak, late-time echoes, faint repeats of the main ring-down. Several teams have searched data from LIGO and Virgo for such echoes. A few studies have reported hints, while others find no convincing evidence. The signals, if present, sit right at the edge of what current instruments can see, so stronger detectors and more events will be needed to make the case either way. There may be other clues. If matter falls onto a surface, even one buried in deep gravity, a small fraction of the energy might be re-emitted after a delay. That energy would be stretched to lower frequencies by redshift and might show up as an ultra-faint glow. The timing and color of that glow would depend on the shell's properties. In practice, the effect may be far too small to separate from all the other light in a crowded region near a compact object. Another idea compares how fast the innermost part of a disk seems to orbit. A true horizon can sit a hair closer to that inner edge than any physical surface can. The difference is tiny, and measurements are messy, but with enough precise spectra and images, future instruments might pick up a mismatch. For now, none of these signs are decisive. Even if nature never builds a gravastar, the idea still helps. It shows that there are self-consistent ways to pack mass into a tiny volume without creating a singularity. It gives theorists a laboratory on paper to test how quantum pressure, vacuum energy, and curved space-time interact. It also motivates observers to sharpen their tools, to look for echoes and late glows and small shifts in orbital patterns. Most importantly, it ties into a bigger goal in physics, joining general relativity, which rules gravity and large-scale structure, with quantum theory, which rules atoms and fields. Each is powerful in its own domain. Trouble comes when both extremes meet, as they do in a collapsing core. Gravastars are one of several models that try to navigate that meeting without running into infinities. With that picture on the table, it helps to anchor the discussion in something we know exists and can measure. Neutron stars are close cousins to both black holes and any gravastar-like object. They come from the same kind of stellar death, yet stop just short of the point where gravity completely wins. Their properties tell us how matter behaves when squeezed to densities found nowhere else. A neutron star forms when the core of a dying massive star is not quite heavy enough to cross the final threshold. As the core collapses, electrons are forced into protons, and the two combine to make neutrons plus neutrinos. The neutrinos rush out. What remains is a compact ball, mostly made of neutrons. The collapse halts when two effects push back. One is neutron degeneracy pressure, a quantum rule that says identical fermions particles, like electrons and neutrons, cannot all share the same state. The other is the strong nuclear force, which resists packing nucleons closer than a certain distance. Together, they balance gravity for cores below a few times the mass of the Sunday. The scale is striking. A typical neutron star is about 20 kilometers, or 12 miles, across roughly the size of a city, and yet holds more mass than our Sunday. The surface gravity is immense, around 100 billion to a few hundred billion times Earth's gravity, depending on the mass and radius. If a person could stand on such a surface which they cannot, their weight would not just increase, the pull would crush them into a thin film in a tiny fraction of a second. A teaspoon of neutron star matter, if somehow kept stable on Earth, would weigh about 1 billion tons. These numbers are not for drama. They follow directly from the star's compact size and mass. Neutron stars also spin fast and carry strong magnetic fields. Some are observed as pulsars, which are rotating neutron stars that sweep beams of radio or X-ray light past us like lighthouse beams. The regular ticks help us measure their rotation with great precision and reveal changes in spin when the star rearranges its crust or exchanges angular momentum with its interior. These details, though beyond today's focus, remind us that neutron stars are active and complex, not static balls. Inside, the structure is layered in ways unlike any planet or ordinary star. The outermost layer is a thin atmosphere, only centimeters thick. Below that lies the crust, a solid lattice of nuclei embedded in a sea of electrons. It is like a metal taken to an extreme, with pressures and densities rising quickly as you go down. Deeper in the crust, the squeeze is so strong that nuclei pack closely and start to change shape. Rather than neat spheres, the nuclear matter forms rods, slabs, and other patterns that minimize energy under the pressure. Scientists call this nuclear pasta because the shapes bring to mind spaghetti, lasagna, and gnocchi. The name is playful, but the physics is serious. These structures affect how heat and electrons move, how the crust cracks, and how the star cools. Beneath the pastor layer, the crust gives way to the outer core. Here, the distinction between individual nuclei disappears. Matter becomes a fluid of neutrons with a fraction of protons, electrons, and possibly muons mixed in. The neutrons may form a superfluid, which is a state of matter that flows without friction. The protons may become a superconductor, carrying electrical current without resistance. These quantum states can exist because the temperature, while enormous by everyday standards, is low compared to the energies that set the behavior inside the star. Superfluid neutrons and superconducting protons change how the star stores and transfers angular momentum and magnetic flux. They help explain sudden spin jumps, called glitches, when a pulsar's rotation rate shifts by a tiny amount as interior vortices move and repin to the crust. As pressure rises further toward the center, the composition may change again. The inner core is the least certain part of any neutron star model. Some calculations suggest that at the highest densities, neutrons start to break into their constituent quarks, forming a soup of up and down quarks, and maybe strange quarks, in a state called quark matter. Others propose more complex particles, such as hyperons, which include strange quarks within heavier baryons. Each possibility changes the equation of state, the relation between pressure and density, and therefore changes how big a neutron star can be for a given mass. Observations of very heavy neutron stars around 2 solar masses already rule out some soft equations of state that would not support that much weight. Measurements of star radii through X-ray timing and gravitational wave signals from neutron-star mergers continue to narrow the options. The outer core's fluid also carries heat away through neutrinos, especially in young neutron stars. The cooling history tells us about which reactions are allowed in the dense matter and how quickly they proceed. If direct Urca processes fast neutrino-emitting reactions are possible, a star cools faster. If they are blocked by the need to conserve momentum among available particles, cooling is slower. Astronomers compare model cooling curves to observed temperatures of neutron stars of different ages to infer which processes are active. In this way, the stars become labs for nuclear physics at densities no Earth-based machine can reach. Back near the surface, the crust is not only a static lattice, it can store stress as the star spins down and its shape tries to adjust. When the stress exceeds a limit, the crust can crack in a starquake. The sudden shift can move vortices in the superfluid below, changing how the interior and crust share angular momentum and producing a glitch in the spin rate. The energy release may show up as a small flare of X-rays or gamma rays in magnetars, which are neutron stars with super strong magnetic fields. These details connect the microphysics of dense matter to signals we can see across the galaxy. In all these layers, gravity sets the stage and quantum rules write the script. Degeneracy pressure holds up the star where ordinary thermal pressure would fail. Nuclear forces shape the crust and the pastor. Superfluidity and superconductivity emerge in the core. The densities, pressures, and magnetic fields are extreme, yet the ideas used to describe them grow from the same physics that explains metals, magnets, and liquid helium, stretched to a scale and intensity we cannot make on Earth. The path from Gravastar models back to neutron stars is not a detour, it's a check on what we already know. Neutron stars show that collapse can stop without a horizon when quantum pressure and nuclear forces are strong enough. They also mark the point where our knowledge thins, because we don't yet know what happens at the very highest densities. That is where ideas like quark matter and, further along the collapse path, alternatives to black holes enter the discussion. By measuring neutron star masses, sizes, spins, cooling, and quakes, we trace the boundary between stable matter and the unknown. Mapping that boundary sets clear targets for the next observations and the next tests of matter under pressure, beyond the crust, through the pastor layer, and into the flowing outer core, where familiar particles begin to give way to a dense quantum sea. Deep inside a neutron star, the pressure rises far beyond anything inside an atomic nucleus. Neutrons are squeezed so tightly that their edges blur and the empty spaces of normal nuclei disappear. At the very center, the inner core conditions exceed what we can reproduce in the lab. Models disagree on what forms there. Some point to matter that includes strange quarks, which are rare in everyday matter. Others suggest a quark-gluon plasma, a hot, dense fluid where quarks move freely and gluons are no longer trapped inside protons and neutrons. That state would resemble the early universe in its first moments, before matter settled into familiar particles. Neutron stars also carry magnetic fields that rank as the strongest known in the universe. On Earth, a magnet turns a compass needle. Around a neutron star, the field is so intense that it can change how atoms themselves are shaped. A typical neutron star's field is about 1 trillion times stronger than Earth's. In a special class called magnetars, the field is another 1,000 times stronger still. Fields at that scale store vast energy. When the crust, the star's rigid outer layer, can no longer support the stress the field places on it, it shifts or cracks. These sudden breaks are starquakes. The quake can jolt the magnetic field, release high-energy light, and slightly change how the star spins. Many neutron stars rotate at remarkable speeds. Some complete hundreds of turns each second. We call these pulsars. Their magnetic poles do not line up with their spin axis, so the field drives beams of radiation out at an angle. As the star turns, the beams sweep across space like the beam from a lighthouse. If Earth sits in the sweep path, we detect a pulse of radio waves, X-rays, or gamma rays at each rotation. The timing can be astonishingly steady. A few pulsars keep time with a stability that rivals atomic clocks. Because the pulses cross the galaxy, astronomers have studied how to use networks of pulsars as a kind of natural GPS for deep space, a quiet rhythm that future spacecraft could follow. How we found these objects is part of modern astronomy's story. Neutron stars were proposed in the 1,930 seconds after scientists discovered the neutron. The math said they could exist, but many thought nature would never push matter that far. Then, in 1967, graduate student Jocelyn Bell, now Jocelyn Bell Burnell, was examining radio data recorded on long lines of chart paper. She noticed a repeating signal that did not match known sources. It was so regular that she and her advisor briefly wondered if it might be a message, jokingly labeling it LGM, one for Little Green Men. Soon they found more sources in different parts of the sky. The pattern pointed to rotating, compact objects. Pulsars had been discovered. The Nobel Prize later recognized the finding, but Bell Burnell herself was not included, a decision that remains controversial and often discussed when people talk about credit in science. Neutron stars are also engines for some of the most energetic events we observe. When two neutron stars share an orbit, they slowly lose energy by emitting gravitational waves, ripples in space-time, predicted by Einstein. As energy drains away, the orbit shrinks. The stars spiral closer, moving faster and faster until they collide. The crash is brief but complex. It creates a distinctive gravitational wave signal that detectors like LIGO and Virgo can record. It also produces a kilonova, a fast-rising, bright flare powered by the radioactive decay of freshly made elements. In some cases, a narrow jet forms and releases a short burst of gamma rays that can be seen across the universe if the jet points near our line of sight. These mergers are more than fireworks. They teach us about matter under pressure and about the origin of heavy elements. When the two stars tear material from each other, neutron-rich debris is flung outward. In that debris, free neutrons slam into atomic nuclei faster than the nuclei can fall apart. This chain is the rapid neutron capture process, or R process. It builds elements heavier than iron, gold and platinum, yes, but also lanthanides that shape the kilonova's color and opacity, and radioactive elements like uranium and thorium. The precious metals in jewelry, the platinum that helps clean car exhaust, the iodine needed by the human thyroid, all likely include atoms forged in ancient neutron star collisions and later mixed into the gas that formed new stars and planets. Gravitational wave observations and light from kilonovae work together to probe this physics. The wave signal tells us about the stars' masses and how easily they deform, a property linked to the stiffness of dense matter. The light curve and spectrum of the kilonova reveal which elements formed and how much mass was ejected. By comparing many events, astronomers learn whether mergers alone can explain the galaxy's heavy elements or whether other sources, like rare supernovae, must also contribute. Each detection narrows the range of possible equations of state, the rules that relate pressure, density, and temperature inside these stars. The inner life of a single neutron star is also a window into unfamiliar states of matter. The crust sits atop a region where pressure reshapes nuclei into rods and slabs, the nuclear pasta layer. Below that, in the outer core, matter flows as a quantum mix of neutrons, protons, and electrons. Neutrons are likely in a superfluid state, which flows without friction. Protons may be superconducting, carrying current with zero resistance. These states allow the star to store angular momentum in arrays of quantum vortices and to trap magnetic fields in thin tubes. When vortices shift or unpin from the crust, the star's rotation can jump slightly, a glitch. When flux tubes move, the magnetic field can change structure and release energy. These small effects, measured as tiny changes in pulse timing or short bursts of X-rays, link quantum behavior to global motion in a way we can observe from light years away. At greater depth, models split. Some predict that as density rises, neutrons dissolve into their smaller parts and form quark matter, a fluid of up, down, and possibly strange quarks. Others allow heavier particles called hyperons, which include strange quarks bound inside baryons. Each option changes how compressible the star is. Observations of neutron stars close to or above twice the mass of the Sun already rule out very soft equations of state that would collapse under that weight. Radius measurements from X-ray timing missions and signals from neutron star mergers add more constraints. Bit by bit, the range of allowed interior models shrinks, though the very center remains uncertain. These questions lead naturally to another idea: quark stars. If pressure breaks neutrons apart, could a star exist where quarks move freely, almost everywhere inside? To reach that idea, it helps to review how matter is built. Atoms contain electrons orbiting a nucleus. The nucleus holds protons and neutrons. Protons and neutrons are not elementary. They are made of quarks bound by gluons the carriers of the strong force. Under normal conditions, quarks are confined. The farther you try to pull them apart, the stronger the force becomes, like a rubber band that fights harder as it stretches. That is why you never find a lone quark in isolation. Inside a neutron star, however, pressure keeps rising as you move inward. At a certain critical density, the energy cost of keeping quarks confined might exceed the cost of letting them roam. If that happens, neutrons would dissolve into a quark fluid. Matter in this state is called quark matter. A star made mostly of quark matter is a quark star. Some versions include a thin crust of normal nuclei above a quark core. Others are quark matter all the way to the surface. Because quark matter packs more tightly, a quark star could be smaller than a neutron star of the same mass, perhaps by tens of %. The surface gravity would be even higher. The magnetic field could reach comparable or greater strengths depending on how the interior organizes currents. One especially interesting case involves strange quark matter. Ordinary protons and neutrons contain up and down quarks, but quarks come in more types, including strange quarks, which are heavier. Some theories suggest that when densities and pressures are high enough, a mix of up, down, and strange quarks could be more stable than any arrangement of just up and down quarks. If true, this strange matter might be the most stable state of matter, the ground state. In that picture, once matter converts to strange quark matter, it prefers to stay that way. Small drops of it, sometimes called strangelets, could in principle exist, and large bodies could be wholly composed of it. Whether nature actually makes this state in stars remains unknown. Experiments at particle colliders reach high temperatures, but not the same cold, crushing pressures found in compact stars. So the question sits with theory and with astrophysical clues. If quark stars exist, how would we tell them from neutron stars? The differences are subtle. For the same mass, a quark star would be smaller, changing how quickly matter can orbit at the inner edge of an accretion disk and slightly shifting the frequencies of vibrations after a starquake or after a merger. Cooling rates might differ because quark matter can allow faster neutrino emission through reactions forbidden in normal nuclear matter. Some glitches might behave differently if the interior vortices move in a quark superfluid rather than a neutron superfluid. In mergers, the tidal deformability, the ease with which a star is squashed would be lower for a more compact star. Gravitational wave data already measure this property, and future detectors with higher sensitivity will sharpen the test. Strange quark matter may carry its own signatures. If it is truly the most stable form, then in some models, a piece of strange matter touching normal nuclear matter could trigger conversion. That sounds alarming, but if such runaways were easy, we would likely see many more signs in nature. The lack of clear evidence sets limits on how these processes work and how stable strange matter would be in real stars. Measurements of very massive neutron stars also push models towards stiffer behavior, which affects whether strange matter would appear at all inside stable stars. Across all possibilities, dense nuclear matter, quark matter, or strange matter, the same basic rules guide the search. Gravity compresses, quantum physics resists or rearranges. Magnetic fields store and release energy. Rotation organizes the interior and shows up as steady pulses. Collisions write their story into space-time and into the periodic table. As timing improves, more mergers are recorded and more kilonova spectra are taken. The range of allowed models narrows and the picture of these cores gets clearer. Returning to the strange matter hypothesis itself, it extends quark matter one step further. It proposes that a mix of up, down, and strange quarks could be more stable than the nucleons that make ordinary atoms? If so, contact between normal nuclear matter and strange matter might trigger conversion. A tiny seed, a strangelet, could, in theory, turn nearby nuclei into strange matter and grow step by step. The idea sounds like fiction, but it follows known rules of the strong force at extreme density. Several safeguards lower the risk. Any strangelets would be rare, lightly charged, or moving so fast they would pass through Earth's atoms without sticking. Collider experiments and cosmic ray studies show no sign of easy conversion, which sets limits on how such seeds behave. The topic remains serious in theory, but the expected risk is extremely low. Because quark matter and strange matter change how dense cores behave, some researchers have proposed that a few compact stars on our lists might be quark stars wearing a neutron star face. The differences would not jump out in a picture. They would hide in careful measurements. A slightly smaller radius for the same mass, a different cooling curve as neutrinos carry heat away, or a distinct response to tidal forces during a merger. As timing arrays, X-ray missions, and gravitational wave detectors improve, the space of possibilities tightens. A confirmed outlier too compact for any normal nuclear model would be a strong hint that quark matter has appeared in nature. The arc of stellar lives includes a quieter end as well. Most stars do not become neutron stars or black holes. They grow old and fade into white dwarfs. This is the path our sun will follow. When a sun-like star runs low on hydrogen in its core, fusion slows, the core contracts, and the outer layers expand and cool. The star becomes a red giant. Over time, gentle winds and pulses lift the outer layers into space, forming a glowing shell of gas, a planetary nebula. The exposed core, now small and hot, settles as a white dwarf. A white dwarf is about the size of Earth, yet can hold roughly half the sun's mass. The density reaches around 1 million times that of water. The support against gravity does not come from heat. It comes from electron degeneracy pressure, a quantum effect rooted in the Pauli exclusion principle. No two electrons can share the exact same quantum state. When electrons are packed very tightly, many are forced into higher energy states simply because the lower ones are already filled. This crowding creates pressure that depends on how tightly the electrons are packed, not on the temperature. That pressure balances gravity and stops further collapse. Newly formed white dwarfs are hot, with surfaces that can exceed 100,000 degrees. With no fusion in the core, they cool slowly over billions of years, like embers fading in a long night. The universe has not existed long enough for any to cool to true black dwarfs, so all white dwarfs we see are still shedding heat. Some white dwarfs live in pairs and draw gas from a companion. The gas spirals in through a disk, piles up on the white dwarf's surface, and eventually reaches a point where hydrogen fuses in a thin layer. The result is a nova, an outburst that brightens the system for days or weeks. The white dwarf survives, and the cycle can repeat many times. There is a limit to how much mass a white dwarf can carry. As the mass grows, the electrons must move faster to produce enough degeneracy pressure, near about 1.4 times the sun's mass. The Chandrasekhar limit the electrons would need to move at the speed of light, which they cannot. If a white dwarf approaches this limit by accreting gas or by merging with another white dwarf, it becomes unstable. Carbon and oxygen in the core ignite in a runaway reaction that burns the star from the inside out. The result is a Type Ia supernova. Unlike core collapse supernovae from massive stars, Type Ia events leave no core behind. The white dwarf is unbound. Their peak brightness is remarkably uniform after simple corrections, which makes them reliable distance markers. In the late 1990 seconds, teams measuring distant Type Ia supernovae found they were dimmer than expected for a slowing universe. The data pointed to an expansion that is speeding up. That observation led to the idea of dark energy, an unknown component of the cosmos that acts with negative pressure on large scales. Turning back to the most compact objects, black holes remain central to the discussion because they define the extreme limit of gravitational collapse. A black hole forms when matter is pressed beyond any support that quantum pressures can provide. The fabric of space-time wraps so tightly that a boundary appears, the event horizon. This is the surface where the escape speed equals the speed of light. No rocket, no signal, no particle moving at or below light speed can climb out once it crosses that boundary. All future paths lead inward toward the center. Inside the standard model of a black hole, matter continues to compress until our equations point to a singularity, a point of zero size and immense density. The singularity is a sign that our theory is being used beyond its tested range. Yet, the exterior predictions are solid. Black holes curve light, slow time near them, and shape the orbits of stars in ways we measure. They power disks that shine in X-rays and can launch jets that extend for light years. When two black holes merge, the final object emits a ringing pattern of gravitational waves that matches general relativity with high precision. Black holes come in several mass ranges. Stellar mass black holes, the remnants of heavy stars, typically weigh from a few to a few tens of suns. We find them in X-ray binaries, where they pull gas from a companion star, and in the mergers that produce gravitational waves. Supermassive black holes sit at the centers of galaxies. They weigh millions to billions of suns. We infer their presence from the orbits of nearby stars, from bright accretion flows in active galactic nuclei, and from the direct images of their shadows against glowing gas. Between these two ends lies the intermediate mass range, from roughly 100 to 100,000 suns. Evidence for these is growing through star cluster dynamics and a few gravitational wave events, but they are harder to confirm because they are rarer and often lack bright accretion. There is also a speculative class, primordial black holes. These would have formed in the early universe from density fluctuations if conditions were right. They could be as small as mountains in mass or larger, but no confirmed detection has been made. Surveys of microlensing events and cosmic backgrounds limit how many could exist in various mass bands. The physics behind black hole sizes ties directly to how they form. Stellar mass black holes come from core collapse when mass and fallback are so large that even neutron degeneracy and nuclear forces cannot halt gravity. Intermediate mass black holes may grow through repeated mergers inside dense star clusters or by the direct collapse of massive gas clouds. Supermassive black holes likely began as heavy seeds in the early universe, then gained mass by swallowing gas and merging with other black holes as galaxies collided. Their growth links to galaxy evolution. The inflow that feeds a central black hole can trigger bursts of star formation, and the energy it releases, radiation, winds, and jets, can heat or expel gas, slowing new stars from forming. Across white dwarfs, neutron stars, quark star candidates, and black holes, the same themes repeat. Gravity pushes inward, Quantum rules resist or rearrange matter into new states. Magnetic fields store energy and stress, crusts and disks. Rotation organizes beams and pulses, turning compact stars into precise timekeepers. Collisions write signatures into gravitational waves and into the heavy elements we mine on Earth. Each instrument adds a layer: radio arrays, time pulsars to microseconds. X-ray telescopes weigh and size compact stars. Optical surveys catch kilonovae as they rise, and interferometers feel space-time stretch. Step by step, these measurements narrow what can lie inside nuclear matter, quark matter, or something more exotic, and test whether horizons always form, or whether, in rare cases, a surface like a Gravastar's shell could replace them. Time near a black hole does not flow like it does in open space. Strong gravity slows clocks. Gravitational time dilation. Far away, a clock ticks normally. Closer in, the same clock runs slow compared with a distant one. Watching safely from afar, you'd see a falling person move in slow motion. Their light shifts to redder colors and fades. On your screen, they never quite cross the event horizon. For the person falling, their own clock stays true. They pass the horizon in finite time, noticing nothing special at that boundary. The danger comes later, as tidal forces the stronger pull at the feet than at the head grow extreme, stretching the body into narrow strands. Spaghettification. Gravity, acting on small and large scales at once. Black holes are not perfectly black in theory. In the 1,970 seconds, Stephen Hawking showed that quantum fields near the horizon allow pairs of particles to form and separate. One escapes to space as radiation, the other falls in. To a distant observer, the whole glows very faintly. This Hawking radiation carries away energy, so the black hole slowly loses mass and will, in principle, evaporate. For black holes the mass of a star or larger, the temperature is tiny, colder than the cosmic microwave background. The loss is far too slow to notice within the age of the universe. For very small, hypothetical black holes, ones that could have formed in the early universe, the temperature would be higher, and the final stages of evaporation would be fast and bright. None have been confirmed, but the idea guides searches for brief, high-energy flashes. Hawking radiation leads to a deep question about information. Quantum mechanics says information is never destroyed. The exact state of a system evolves in a reversible way. But Hawking's calculation makes the radiation look thermal, like the glow from a hot stove, which carries no memory of what fell in. If a black hole evaporates fully into featureless radiation, where did the details go? This is the black hole information paradox. Many ideas have been developed to square the books. Black hole complementarity suggests that to an outside observer, all the information is stored and processed at or near the horizon, while for the infaller, physics looks normal until very late. The two stories do not need to be combined into one picture because no single observer can see both. The holographic principle goes further, proposing that the information in a volume can be encoded on its boundary, like a hologram. In some models of spacetime, a theory without gravity on a boundary can fully describe a gravitational theory inside. These ideas do not rely on magic. They are attempts to keep unitarity, the no-destruction rule of quantum mechanics, while respecting what we know about gravity. The debate is active, and improved thought experiments, mathematics, and even indirect observations help test which versions make sense. Our view of black holes is no longer only indirect. the Event Horizon Telescope, a network of radio dishes spread across Earth and synchronized to act as a planet-sized instrument, has resolved the silhouette around two supermassive black holes. The image of the object in galaxy M87 shows a bright, lopsided ring with a dark center. The ring is light from hot gas being bent by strong gravity. The dark region is a shadow, not the event horizon itself, but a larger area where light paths fall inward and fail to reach us. A similar image of the compact object at the center of our Milky Way, called Sagittarius A*, shows the same features, adjusted for mass and motion. These pictures match general relativity's predictions for how light behaves near a rotating black hole, including the size of the shadow relative to the mass. They also let scientists test models of how gas plunges in and how magnetic fields shape the flow. Black holes do not sit idle at galaxy centers. When gas falls toward a supermassive black hole, it forms an accretion disk. Friction and magnetic effects heat the gas to extreme temperatures. The disk and its corona can outshine the rest of the galaxy. Some systems launch narrow jets along the black hole's spin axis that blast material outward at speeds close to light. This activity is called an active galactic nucleus. The energy dumped into the surrounding gas can slow or stop new star formation by heating the gas or sweeping it out of the galaxy. Observers also find tight links between the mass of a galaxy's central black hole and the properties of the galaxy's bulge, such as the average speed of its stars. These patterns suggest that the growth of black holes and the growth of galaxies are connected by feedback. The galaxy feeds the black hole. The black hole's output changes the galaxy's gas supply, and the cycle repeats. Step back from single systems, and the map of the universe shows a web of matter, with galaxies gathering along filaments and clusters, where filaments cross. Two large-scale mysteries shape this structure: dark matter and dark energy. Together, they make up about 95% of the cosmic budget. The matter we can see: stars, planets, glowing gas, dust, and all the light accounts for the remaining 5%. The dark part was not added for drama. It was added because gravity behaves as if more mass is present than our telescopes can count. In the 1,930 seconds, Fritz Zwicky studied the Coma cluster and found its galaxies moving faster than the visible mass could bind. He argued that unseen matter must be holding the cluster together. The idea did not catch on widely at the time. Decades later, Vera Rubin and collaborators measured how fast stars orbit in spiral galaxies. If most of the mass were in the bright disk, then stars farther out should orbit more slowly, as outer planets do around the Sunday. Instead, Rubin found flat rotation curves. Stars in the outer parts move almost as fast as those near the center. The natural reading is that galaxies sit inside massive halos of dark matter that extend far beyond the visible disk. Evidence grew from other angles. Gravitational lensing, the bending of light by mass, lets astronomers map how mass is spread, whether it glows or not. In clusters, the lensing pattern shows more mass than the hot gas and stars can explain. The cosmic microwave background, the faint afterglow of the Big Bang, carries tiny ripples in temperature across the sky. The size and strength of those ripples are sensitive to how much ordinary matter and dark matter filled the early universe. The data point to a universe with about 5 times more dark matter than ordinary matter. On larger scales, the way galaxies cluster also matches models that include dark matter as a backbone. Each method has different systematics, yet all lean the same way. What then? is dark matter made of? It is not atoms, not the faint glow of dust, not cold gas that failed to light up. It does not absorb or emit light, and it does not collide strongly with ordinary matter, or we would have seen it in detectors already. The leading ideas focus on new particles that were made in the early universe. One family is WIMPs, weakly interacting massive particles that feel gravity and the weak nuclear force, but not the electromagnetic or strong forces. Another idea is the axion, a very light particle that could act as a field spread through space. Both ideas have motivated experiments. Deep underground, detectors watch for the tiny recoil of a nucleus hit by a passing dark matter particle. Telescopes search the sky for gamma rays that might come from dark matter particles meeting and annihilating each other. Radio and microwave cavities in strong magnetic fields listen for axions turning into photons. So far, no clear signal has appeared. Each null result trims away part of the possible mass and interaction strength. The search continues with more sensitive instruments and new methods. Because these searches have not yet found a particle, some physicists ask whether gravity itself needs adjustment on large scales. Modified gravity theories try to fit galaxy motions without adding unseen mass. The most discussed version is Mond-modified Newtonian dynamics, which tweaks the law that links force and acceleration at very low accelerations, like those felt in the outskirts of galaxies. Mond can match many galaxy rotation curves, with fewer free choices than a dark matter halo model, but it struggles with clusters of galaxies, with the pattern of the cosmic microwave background, and with systems like the bullet cluster, where the mass mapped by lensing sits apart from the hot, X-ray emitting gas after two clusters collided. More sophisticated versions build full relativistic theories to handle lensing and cosmology, and these are tested against the same data. At present, the weight of evidence favors dark matter as an added component, while modified gravity remains a useful tool to probe where our models might miss details. Dark energy is the other unseen player. Its effects show up in the way the expansion of the universe speeds up over time. Type Ia supernovae, used as distance markers, appear dimmer than they would in a universe that was slowing down. The pattern of ripples in the cosmic microwave background and the distribution of galaxies across large volumes reinforce this picture. In the simplest model, dark energy acts like a constant energy density of the vacuum with negative pressure, pushing space to expand faster. That model fits many observations. Alternatives include fields that change with time or ideas that alter gravity on very large scales. Whatever the cause, the acceleration means that over very long times, distant galaxies will slip beyond our horizon and the local web will thin. Across these topics, time dilation, near horizons, Hawking radiation and the information puzzle, images of black hole shadows, jets that regulate star birth, and the hidden mass and energy shaping the cosmic web, the same method keeps us grounded. We begin with clear rules, test them where we can, and watch for patterns that repeat across systems. Where rules clash, like quantum mechanics and gravity at a horizon, we look for a larger frame that can hold both. Where data point to something unseen, we build experiments to search for it directly, and models to see what else the same idea would predict. Step by step, the map of the universe gains detail, from the edge of a black hole's shadow to the slow pull of dark matter in a galaxy's outer disk. Mond can match the flat rotation curves of many galaxies with only a few inputs, but it stumbles in places where the whole cosmic picture must hang together. The detailed pattern of the cosmic microwave background, the tiny hot and cold spots across the sky, fits cleanly with dark matter, but is hard to reproduce with simple MOND. So does weak gravitational lensing, where the shapes of many distant galaxies are sheared by foreground mass in just the way dark matter halos predict. Cluster collisions, like the famous bullet cluster, show the mass traced by lensing separating from the hot gas seen in X-rays, which again points to unseen matter rather than a modified law alone. Because of evidence like this, most researchers favor dark matter as a real component. Even so, modified gravity remains useful as a reminder that assumptions should be tested, and it keeps pressure on the data and the models to be precise. Dark energy is an even deeper puzzle. In the late 1990 seconds, two teams measured the distances to faraway Type Ia supernovae to see how the universe's expansion was changing. Gravity should slow the expansion over time if matter were the only player. The supernovae told a different story. They appeared dimmer than expected, which means farther away than a slowing universe would allow. The expansion is speeding up. Something pushes space apart, and we call that dark energy. A key clue is that dark energy acts like a property of space itself. As space expands, there is more of it, so the effect does not thin out the way matter does. The result is a gentle but persistent push that becomes more important as the universe grows larger and matter spreads out. Today, the best fit numbers say about 68% of the cosmic energy density is dark energy, about 27% is dark matter, and only about 5% is the ordinary matter that makes stars, planets, and people. The simplest way to describe dark energy is Einstein's cosmological constant, a constant energy density of the vacuum. Einstein once added this term to make a static universe and later called it a blunder when expansion was discovered. Ironically, a constant energy of the vacuum fits the current data very well. Vacuum energy connects to quantum fields. Even empty space hums with tiny fluctuations, and that hum carries energy. On paper, we can try to add up the contributions from known fields. The result is shocking. The simple sum is larger than the observed dark energy by roughly 10, 100, and 20. This mismatch, often called the worst prediction in physics, tells us that we do not yet know how vacuum energy should be counted in a full theory. That gap fuels other ideas. One is quintessence, a slowly changing field whose energy density can vary over time. Another is that gravity itself changes on the larger scales. So what looks like extra energy is really a shift in how space-time responds to mass and pressure. Upcoming maps of galaxies and supernovae across cosmic time will help. If dark energy is a true constant, the history of expansion will follow one curve. If it changes, the curve will bend in a different way. Small differences, measured with care, can sort the options. To understand how extreme objects formed, we trace the story back to the beginning. The universe is about 13.8 billion years old. At the start, it was hot and dense, beyond anything we can make in a lab. In the first instant, matter as we know it did not exist. The contents were a plasma of quarks and gluons, along with other fundamental particles moving in a fierce bath of radiation. As the universe expanded, it cooled. Within a few microseconds, quarks locked together to make protons and neutrons. About 3 minutes later, the temperature dropped enough for some of those protons and neutrons to fuse into small atomic nuclei. This first round of nuclear building, called Big Bang nucleosynthesis, made mostly hydrogen and helium with a trace of lithium. Even then, atoms were not yet possible. Free electrons were everywhere, and photons, particles of light, kept bouncing off them, like beams of light scattering off fog. The universe was opaque. Only after about 380,000 years did the temperature fall enough for electrons to attach to nuclei and make neutral atoms. This step is called recombination. With electrons bound, photons could fly across space without constant scattering. The fog cleared. The light from that time has been traveling ever since, stretched by expansion into microwaves. We see it today as the cosmic microwave background, a nearly uniform glow across the sky with tiny ripples only 1 part in 100,000. Those ripples are the imprint of the first density variations, and they are a goldmine of information about the early universe. Yet the very smoothness of the microwave background posed a puzzle known as the horizon problem. Regions on opposite sides of the sky have almost exactly the same temperature, but they are so far apart that in a simple Big Bang picture without any special early phase, no signal could have crossed between them to even out their temperatures. How did they agree to be so similar? The flatness of space is another puzzle. The geometry we measure is very close to flat, which is a delicate state. Small deviations from flatness would normally grow over time, but we do not see those deviations today. Cosmic inflation was proposed to answer these puzzles. Inflation is a very brief period of extremely rapid expansion in the first sliver of a second. During this phase, the universe doubled in size many times over. A small region that was in thermal contact before inflation could have been smoothed to a uniform temperature, and inflation then stretched that uniform patch to a size larger than the observable universe. That explains the evenness of the microwave background without any communication across the sky after the fact. Inflation also takes any initial curvature and flattens it out, like stretching a wrinkled sheet until it looks flat over a small area. Quantum physics plays an unexpected role here. On tiny scales, fields fluctuate. During inflation, those tiny fluctuations were blown up to cosmic scales. Small bumps in density became the seeds of the later structure. After inflation ended, gravity made the slightly denser regions pull in more matter. Over time, they grew into clouds, then stars and galaxies, and finally, the web-like structure of clusters and filaments we map today. The statistical pattern of those first bumps, how strong they are at different sizes, can be read from the microwave background and from the clustering of galaxies. The match between those patterns and simple inflationary models is one of the reasons inflation is widely used in cosmology. What drove inflation? The leading idea uses a scalar field called the inflaton. A scalar field is a field with a value at every point in space, like temperature in a room, while the inflaton sat high on its energy curve. Its energy density behaved like a near-constant vacuum energy and drove rapid expansion. The field then rolled down its curve, inflation ended, and the stored energy dumped into ordinary particles and radiation. This step is called reheating. It refilled the universe with the building blocks that later made atoms, stars, and planets. Different inflaton models choose different curves and predict slightly different patterns in the microwave background and in the distribution of galaxies. Precision measurements press on those predictions, ruling out some and keeping others alive. Inflation also suggests a way to link tiny quantum effects to large cosmic features. Because the fluctuations were quantum in origin, the universe's largest structures carry a record of quantum randomness from the earliest times. That is a striking chain. Quantum wiggles, blown up by inflation, become the scaffolding for galaxies and galaxy clusters. In some models, Inflation can even produce a background of gravitational waves ripples in space-time from the earliest moments. These primordial waves would leave a special twist pattern, called B modes, in the polarization of the microwave background. Experiments are searching for this twist. A detection would be a powerful clue to the energy scale of inflation. A non-detection keeps tightening the limits and guides theorists toward shapes of the inflaton field that produce weaker waves. As the universe cooled further and neutral atoms formed, gravity took over the slow work of structure building. Dark matter, which does not lose energy by emitting light, clumped first. Ordinary gas then fell into the dark matter wells, cooled by emitting radiation, and formed the first stars. The first galaxies lit up, clustering along the filaments made by dark matter. Black holes grew in the densest centers. Star formation and black hole activity lit and heated the gas, while supernovae and jets pushed it around. This feedback-based dance has continued for billions of years, setting the stage for the compact objects and mergers we now observe with telescopes and gravitational wave detectors. Throughout this history, the same themes repeat at different scales. Fields and particles obey quantum rules. Gravity shapes space-time. Pressure, temperature, and expansion compete and trade roles as conditions change. Vacuum energy may act as a gentle push on the largest scales, while degeneracy, pressure, and nuclear forces set the behavior of dense stars. Inflation smooths and seeds the early universe, while later, small variations grow into the rich structure we see. The light that left when atoms first formed still arrives, carrying a nearly perfect snapshot of conditions then. The heavy elements forged in neutron star mergers end up in planets and bodies, and in the deepest wells of gravity, time slows, light bends, and horizons test the edges of our theories. Looking ahead, the far future of the universe depends on dark energy and on the overall shape of space. If dark energy stays constant, as current data suggest, expansion will not slow. It will speed up. Distant galaxies outside our local group will move away so quickly that their light can never reach us again, not because they break the light speed limit, but because space between us and them stretches faster than light can cross. They slip beyond a cosmic horizon. In that remote era, observers would see only the remnant of the local group, bound together by gravity, with no direct sign that a larger universe ever existed. Starbirth will continue while cold gas lasts, then fade as the supply runs down. The long-lived red dwarfs, the smallest stars, will burn for trillions of years before cooling. After the last stars die, the universe enters a degenerate era ruled by stellar corpses, white dwarfs, neutron stars, and black holes. White dwarfs will cool and crystallize, their interiors forming vast lattices of carbon and oxygen. Neutron stars will slowly lose heat and spin. Black holes will dominate the mass budget because they are so compact and long-lived, but even they are not permanent. On very long timescales, quantum effects make change unavoidable. Protons may be unstable, though no decay has been seen. Some theories allow lifetimes around 10-40 years or longer. If protons decay, matter slowly dissolves into lighter particles. Black holes, meanwhile, emit Hawking radiation. The smaller the hole, the faster the loss. A black hole with the mass of a star would take about 1067 years to evaporate. The most massive black holes at galaxy centers, weighing millions to billions of suns, would last up to about 100 years. Their final moments would be brief and bright compared with the slow ages before them. ending in a last burst of radiation. After the last evaporation, the contents thin to a cold mix of low-energy photons, neutrinos, and a sparse gas of the lightest particles, with temperatures drifting close to absolute zero. Structure fades. With no free energy left to drive new change, the universe sits in a state of maximum entropy. This heat-death picture is simple and follows from constant dark energy and an open or flat geometry. Other paths remain possible if dark energy behaves differently. If its push grows stronger with time, the expansion could run away in a big rip. Gravity would lose its hold first on clusters, then on galaxies, then on star systems. At a set time in the future, determined by how rapidly dark energy increases, even atoms could be pulled apart as the scale of space doubles faster and faster. If, instead, dark energy weakens and the matter density is high enough, gravity could reverse the expansion. The Big Crunch would bring galaxies together, raise temperatures, and compress radiation to shorter wavelengths. In some scenarios, the collapse could rebound into a big bounce, starting a new expansion. These alternatives depend on how dark energy evolves and on the exact energy balance of the universe. Observations today point to a flat or nearly flat geometry and to dark energy that behaves like a constant. Galaxy maps, supernova distances, and the microwave background favor an expansion that lasts without reversal, with no sign that the push is changing with time. Still, limits leave room for slow drift, so new surveys aim to track the expansion history more tightly and to watch how structures grow under the pull of gravity and the push of dark energy. Across these futures, the timetable is set by known physics and by a few key unknowns. Star formation relies on cooling gas. Once used, it is not easily replaced. Stellar remnants cool by radiation and by neutrinos early on, then sit for long ages. Black holes evaporate so slowly that their lifetimes dwarf the current age of the universe. If protons are stable, matter survives far longer. If not, decay adds another slow fade. The only lever that can change the destiny in a large way is dark energy, because it sets the global expansion. The steps that lead to that distant future connect back to the compact objects already in view. White dwarfs are the quiet embers of sun-like stars. Their cooling paths help calibrate ages of star clusters and match the expectation that small stars last longest. Neutron stars and black holes mark the end of heavy stars, and their mergers feed the heavy elements back to galaxies. Over time, fewer new stars form from recycled gas, and more mass sinks into remnants. As galaxies age and interact, supermassive black holes at their centers grow by accretion and mergers, locking more mass into objects with the longest lifetimes. The balance shifts slowly from bright, short-lived phases to dark, stable ones. If the expansion continues to accelerate, the large-scale structure will also change. Today we see a cosmic web, filaments of dark matter and gas with clusters at their nodes. As space stretches, the filaments thin and the flow of matter into clusters slows. Within bound clusters like our local group, gravity still rules and stars still orbit. Beyond the horizon, new light never arrives. The sky's deep background becomes simpler as the cosmic microwave background cools and redshifts to wavelengths far beyond any practical detector. For any future astronomer without access to ancient records, the clues that led us to a hot Big Bang and a rich web of galaxies would be missing. Even in a quiet universe, quantum processes continue. Tunneling, decay, and rare interactions slowly shift the mix of particles. If a particle of dark matter is unstable on ultra-long timescales, its decay products would add to the low-energy bath. If dark energy is a field with more than one state, it could, in principle, tunnel to a different vacuum with different properties, though such ideas are speculative and constrained by the fact that our vacuum has been stable for billions of years. Each of these options is testable in part by watching how the universe expands and structures grow today, and by measuring particle properties in the lab. The language for these timelines may sound abstract, but the logic is straightforward. Entropy counts how many microstates match a given macrostate. Systems with no input of free energy drift toward states with more available arrangements. Stars fight that drift by fusing nuclei and releasing energy until their fuel ends. Accretion disks around black holes turn gravitational energy into heat and light until the gas is gone. When the engines stop, the rest is bookkeeping set by quantum rules and by the expansion of space. The questions that remain are clear and concrete. We do not yet know whether dark energy is exactly constant or slowly changing. We do not know the nature of dark matter, which affects how structures formed and how they will age. We do not know if protons decay, which controls how long ordinary matter persists. We do not know if rare compact objects, such as primordial black holes, play any role in the long-term mass budget. And we do not know whether new physics appears at scales or energies we have not yet reached, which could alter any of these forecasts. Progress over the last century shows that these questions are approachable. The age and size of the universe moved from speculation to measurement. The cosmic microwave background was predicted and then mapped in detail. The link between supernova brightness and distance turned into a tool that revealed accelerating expansion. The masses of compact objects are measured through their orbits and their light. Gravitational waves opened a new channel, letting us time the last seconds of mergers and weigh the remnants precisely. Radio, optical, X-ray, and gamma-ray telescopes track the flow of matter into and out of galaxies and the growth of black holes. Each new dataset narrows the options for the future as well. Better supernova surveys and galaxy redshift maps refine the curve of expansion. Weak lensing maps trace how dark matter clumps, testing models of gravity and dark energy at the same time. Pulsar timing arrays listen for the slow background hum of giant black holes merging over cosmic time. Laboratory searches for dark matter particles and for proton decay push limits downward, ruling out classes of models or guiding new ones. The same approach extends to compact object alternatives. Searches for ring-down echoes test whether horizons act as perfect one-way surfaces. Measurements of neutron star sizes and tidal responses press on the equation of state of dense matter. Timing of pulsars prize open the interior physics through glitches and cooling. The outlook, then, is practical. The long-term fate follows from a few inputs we can measure or bound: geometry, the behavior of dark energy, the stability of particles, and the physics of black holes. If those inputs hold as they appear today, expansion continues, star-making slows, remnants rule, and Hawking radiation ends the last structures at staggeringly late times. If any input changes, if dark energy evolves, if decay channels open, if new interactions turn on, the path can shift in defined ways. Mapping which measurements control which parts of the story helps set goals for the next generation of observatories. The same map also keeps extreme ideas in check. Claims about rips, bounces, and new vacua have clear signatures to seek. changes in the rate at which structures grow, departures from a constant dark energy, relic gravitational waves with specific patterns, or sudden events that would leave sharp marks in cosmic backgrounds. While none are seen so far, the search is valuable. It tests the edges of our models and ensures that the story of the future rests on more than assumption. From compact stars to black hole horizons, from the first fractions of a second to timescales that dwarf any human era, the physics connects through a small set of principles. Gravity shapes the stage. Quantum rules set the limits and the exceptions. Thermodynamics points the direction of time for large systems. With those tools, the path from today's universe to its distant phases is not only a tale of extremes, it is a chain of causes that can be calculated, compared to data, and tightened as new evidence arrives. Each generation of researchers stands on the work of the last. New tools and ideas let us test old claims and open new paths. The objects we have followed, black holes, neutron stars, possible gravastars, and the candidates for quark matter, sit at the edges of what nature allows. They show that reality can be both strange and consistent, ruled by math that we can write down and test, even when the results feel unlikely. They also push us to keep asking better questions and to design sharper measurements. There are clear goals on the horizon. We may find faint echoes in gravitational wave data that would point to a surface near where a horizon would be, a sign that some compact objects are Gravastar-like rather than classic black holes. We may isolate a particle that explains dark matter and connects galaxy motion to lab physics. We may build a full theory of quantum gravity that joins general relativity with quantum rules into one framework that works at every scale. It is also possible that an observation will fall outside every current model and force a rewrite. This is not failure. It is how science improves its map. When you look at the sky, you can think of it as a calm picture of stars, or as a set of ongoing experiments. Gravity knots, space around black holes, matter in neutron stars, shows quantum effects on city-size scales. A gravastar, if it exists, would hold a shell in balance with vacuum energy inside. All of this sits within a larger frame of dark matter and dark energy that guide how galaxies grow and spread. The more we measure, the more we see that simple rules can produce very different outcomes under extreme conditions. Reasonable what-ifs help set targets. What if some compact objects do not erase information, but store and re-emit it in ways we have not yet resolved? What if certain forms of matter exist only under the pressures found inside collapsing cores? What if space-time itself has features that change from place to place on very large scales, not only near strong gravity? What if time flows at slightly different rates in wide regions because of fields we have not yet measured? Questions about observation and measurement belong here too. Quantum experiments show that how we set up a measurement changes the results we record. Whether that lesson has any role at cosmic scales is an open topic, best handled by clear models and tests rather than claims. Ideas about wider structures remain speculative but testable in parts. Some models explore a multiverse, many expanding regions, each with its own settings for particle masses or interaction strengths. If such regions can interact, even rarely, they might leave weak signatures, like small, specific patterns in background radiation or unusual alignments in large-scale maps. Signals we now treat as noise may someday be separated into known sources and a new remainder. For now, the evidence for a single expanding universe with dark matter and dark energy is strong, and any extension must match that base. Physics also studies time in careful ways. Some theories allow for branching histories or loops under strict conditions, but these are mathematical tools unless tied to observations. If regions with different, effective rules exist, they would still need to reduce to our known physics where we can test it. The same caution applies to proposed particles that move in unusual ways, or to fields that change the behavior of space over long distances. Each idea sets a prediction. Instruments can then check whether that prediction appears in data. Unfamiliar engines may power objects we have not yet seen. A star could, in principle, run on energy from phases of dense matter rather than standard fusion if stable states exist at the right pressures. A planet-mass object could form from dark matter. If dark matter can clump on small scales, it would be hard to see, but its gravity could be found through lensing or precise motions of nearby stars. Large, organized structures in plasma, guided by magnetic fields over light-year lengths, already occur in jets and nebulae. Whether such structures can carry complex, long-lived patterns is a question for plasma physics and radio astronomy, not only for imagination. The vacuum between galaxies is not empty in a strict sense. Quantum fields fluctuate, and virtual pairs form and vanish. On average, many effects cancel, but small residuals can show up as forces or noise if detectors are quiet enough. Dark energy may be linked to a vacuum term. If it changes with time, that change should leave a record in how the expansion rate curves with distance and in how structure grows. Some theories picture our observable universe as one bubble among many, where collisions between bubbles could imprint circles or asymmetries in the cosmic microwave background. Surveys have looked for such marks and set limits. Continued work will push those limits lower. Upcoming tools aim at these edges. Next-generation gravitational wave interferometers will hear weaker and more distant mergers and may resolve late-time features in ringdowns. Quantum sensors cooled to near absolute zero will probe tiny forces and fields that might couple to dark matter or to new interactions. Neutrino observatories and cosmic ray arrays will collect higher statistics on rare events, letting us sort unusual air showers from true signals of new physics. Radio arrays may map large volumes of hydrogen across time, tightening tests of how structure formed under the pull of dark matter and the push of dark energy. If a result appears that does not fit after checks for error and bias, it becomes a starting point, not a dead end. We expect surprises at boundaries, near singularities, at the Planck scale, and in the earliest instance after inflation. Equations that work well in one regime can break in another, and that is a clue to what is missing. A fuller theory may keep the successes of older ones while adding pieces that only matter at extremes. This is how classical mechanics gave way to relativity and quantum mechanics without losing its role for everyday speeds and sizes. Some proposals stretch our everyday language. Extra dimensions are one example. They can be real in a model's math, while remaining curled up and small, so that we do not notice them directly. Nonlinear time is another. Certain solutions in general relativity allow closed time-like curves under special setups, but nature may block the conditions needed to make them. These are careful distinctions. They keep speculation connected to equations and to tests. Dense matter may still hold surprises. A crystalline form of quark matter, if stable, would change how a compact star vibrates and cools. A dark matter-rich planet would change how a star wobbles and how a background star brightens when it passes behind the object. Large-scale plasma structures leave signatures in polarization and in the timing of radio pulses through a medium. Each of these can be sought with current or near-future facilities. The vacuum itself could hide weak but structured signals. If dark energy is a field that can ripple or cluster slightly, maps of galaxies and lensing could pick out those patterns. If our bubble ever interacted with another, very early on, the microwave background could carry a low-contrast, geometric trace. High-energy particles striking the atmosphere might, in rare cases, carry properties that point to interactions beyond the standard model of particle physics. Sorting real effects from noise requires long campaigns, cross-checks between instruments, and open data where possible. Step by step, instruments improve and theory sharpens. Better timing of pulsars builds a background map of slow gravitational waves from giant black holes merging in distant galaxies. Deeper supernova surveys refine the history of expansion and test whether dark energy is constant or drifts. Laboratory searches narrow the windows for axions and other dark matter candidates. Precision tests of gravity look for small departures from general relativity on large scales while confirming its strength near compact objects. None of this demands that the universe conform to our first ideas. It asks that claims be tied to predictions and that predictions be checked where data are cleanest. In this way, extreme objects stop being only curiosities and become tools. They stress our theories in ways that lab experiments cannot, and they feed back into our basic picture of space, time, and matter. The same compact stars that shake space-time also help set the origin of elements. The same black hole shadows that match relativity guide models of how magnetic fields move energy. The same background radiation that marks recombination holds the imprint of the first quantum fluctuations. As questions grow subtler, the needed measurements become calmer and more exact. Long integrations, stable detectors, and careful calibration matter as much as new ideas. The work is patient. It moves by ruling out whole classes of explanations and by finding small but repeatable differences. The results, when they come, add pieces that may look modest at first, but later become cornerstones. Step by step, the map gains detail. The unknowns shrink or shift to new corners, and the range between what we can imagine and what nature shows us becomes a little narrower, even as new edges come into view. Tools will change as our questions grow sharper. Today we fly metal telescopes and link radio dishes across continents. Tomorrow's instruments may be woven more tightly into the physics they measure. One idea imagines detectors that follow the lines of galactic magnetic fields, sensing ripples in plasma and gravity, the way a stretched string responds to a touch. Another points to swarms of programmable matter, tiny units that rearrange themselves during flight to survive heat, cold, or radiation, reconfiguring antennas and shields on the fly. Some probes could skirt the edges of event horizons, exchanging data in quantum-safe codes that survive the deep redshift near a black hole. Others might treat the cosmic microwave background as a reference frame, using its faint gradients as a guide, the way sailors once used the wind. Navigation itself may shift from traveling through space to changing how space is arranged. A craft that can alter its geometry relative to surrounding space-time would not need long burns or massive fuel. It would switch configurations, matching boundary conditions that favor a new location, much as a page can fold to bring 2 points together. In this view, a journey becomes a transition, limited by control of geometry rather than by thrust. Such ideas sit at the boundary of theory and engineering, yet they set clear tests. Measure how space-time responds to controlled fields, learn which configurations are stable, map the energy costs as precisely as rocket equations once were mapped. Sensing may one day include the human nervous system as a tuned component rather than a mere passenger. The brain is a physical system. It filters signals and finds patterns. With training and feedback, people already improve their sensitivity to faint tones or small visual changes. If paired with quantum-limited instruments and real-time displays, perception could be shaped to recognize specific signatures: the slow swell of a passing gravitational wave, the telltale polarization twist of distant dust, or the noise pattern of axion-like fields in a cavity. This is not mysticism. It is biofeedback and cognition designed to complement machines where pattern recognition matters more than raw power. In nature, birds sense magnetic fields. Fish detect electric fields. Whales communicate across ocean basins. A similar pairing of biology and instrumentation could extend human sensing to space-time curvature or probability flows expressed as stable visual or auditory cues. As tools expand, the channel between universe and observer widens. Gravity waves report on the motion of heavy, compact bodies. Neutrinos carry news from the cores of stars and from violent jets, crossing galaxies almost unchanged. Polarized light traces magnetic fields and dust shapes. Bursts across the spectrum mark shocks and mergers. Solar and stellar winds reveal how hot plasmas move. None of these signals existed for early astronomy. Now, they fill archives by the petabyte. Fluency grows with practice. Calibrate the detectors, remove the foregrounds, compare models to data, and refine the questions. The pattern of progress repeats. From the faintest strain in an interferometer arm to the slow lensing of galaxy images, each new measurement adds a constraint. Where the standard model of cosmology fits, predictions tighten. Where it strains, the strain guides new ideas. Compact objects continue to serve as stress tests. Ring-downs from mergers limit how horizons behave. Pulsar timing arrays sketch a background of long-wavelength gravitational waves from giant black hole pairs. X-ray timing missions track the innermost orbits around dense stars, pinning down the stiffness of matter at nuclear densities. Laboratory detectors listen for dark matter candidates, while colliders map known particles with higher precision. Speculation about the next instruments often points to scales rather than to single devices. An observatory could be a network of nodes spread through the solar system, each with clocks stabilized by optical links. Timing across that baseline would improve parallax, lensing measurements, and gravitational wave sensitivity. A deep space array might place receivers well beyond Earth's radio noise, tuned to low frequencies that ground-based telescopes cannot reach. A constellation could shade itself and cool passively to microkelvin temperatures to cut thermal noise and approach quantum limits on measurement. In particle searches, kilometer-scale underground detectors may be joined by tabletop experiments that exploit new materials, superconducting circuits, and squeezed light to beat down noise. Probes near extreme gravity require new ways to think about communication. Signals sent from just outside a horizon arrive late and redshifted. Quantum encoding using entanglement or error-correcting codes designed for noisy channels could protect information against both radiation and time dilation. Staging relays along safe orbits would trade energy for bandwidth. These are engineering details, but they follow from general relativity's basic map of how light and time behave near compact masses. Even the space between galaxies may become part of a detector. Large-scale surveys already measure how neutral hydrogen absorbs background light, drawing a three-dimensional map of gas across billions of light-years. Future versions could track subtle line shifts that reveal motions within filaments and sheets of the cosmic web. Weak lensing maps will grow denser, tracing how dark matter clusters and how that clustering changes with time. If dark energy drifts from a constant to a field that evolves, those maps will curve in a new way. If gravity changes form on the largest scales, the growth of structure will betray it. At the same time, careful design keeps imagination tethered to tests. A spacecraft that folds space-time must obey energy conditions or show clearly how those conditions are bypassed. A swarm that adapts mid-flight must carry control laws that remain stable amid noise and delay. A human-in-the-loop sensor must be tested with blind injections and controls to confirm that patterns recognized by the brain reflect real signals, not bias. The point is not to slow invention, but to make each step reproducible, so that others can build on it, and so that negative results are as informative as positive ones. Looking across messengers and methods, the universe speaks in many dialects. Gravity provides a slow, deep bass. Light fills a broad middle band from radio to gamma rays. Particles, cosmic rays, neutrinos arrive as rare, high-energy notes. Each channel carries its own distortions. Dust polarizes light. Earth's atmosphere bends and blurs. Magnetic fields scramble particle paths. Instruments and analysis correct for these effects by measuring them directly. Map the dust, monitor the weather, model the fields, and use redundancy across instruments to isolate what is common. The frontier is not only at high energy or strong gravity, it also lies in quiet. Tiny frequency shifts in atomic clocks test whether fundamental constants drift. Small deviations in planetary orbits test gravity in the weak field slow motion regime. Stable resonators listen for high-frequency gravitational waves that lie above the reach of kilometer-scale interferometers. Ultra-sensitive torsion balances look for forces beyond the four we know. These quiet measurements complement the dramatic images of black hole shadows and the spectacular chirps of merging neutron stars. As knowledge grows, language tends to simplify. Terms like vacuum energy, degeneracy pressure, and curvature started as abstract ideas. They now connect to data. The Hubble diagram of supernovae for cosmic acceleration, white dwarf masses, and radii for electron degeneracy, lensing arcs for curvature's effect on light paths. Future terms may follow the same path. Programmable matter today means reconfigurable materials and structures. Tomorrow, it could mean a standard class of self-assembling components with known failure modes and performance curves. Geometric reconfiguration may move from speculation to an engineering discipline with textbooks and simulations. Instruments do more than confirm theories. They reveal surprises. The first radio surveys found sources brighter and stranger than expected. X-ray satellites revealed hot halos around galaxies and clusters. Gravitational wave detectors are now catching mergers that produce masses and spins not seen before. Each time, the map of what is common versus rare changes. Planning for the next step means designing for discovery, wide fields to catch the unexpected, fast response to follow up transients, and open data to allow independent checks and creative new uses. The role of people in this process is practical. Teams need skills that cross boundaries: physics to set targets, engineering to build hardware, software to handle data, statistics to separate signal from noise, and operations to keep systems stable for years. Training emphasizes both depth and translation, the ability to explain a method clearly across fields. International networks share sky coverage and night-day cycles. They also share failure modes and lessons learned. The work is patient and cumulative. Even very bold ideas can be framed in testable ways. If detectors could ride the gradients of the cosmic microwave background for navigation, simulations can quantify drift and error under realistic noise. If quantum encodings can survive near a horizon, testbeds can be built with analog systems that mimic time delay and loss. If human perception is added to the loop, controlled studies can measure improvement over machine-only pipelines. Results define whether an idea moves forward, changes shape, or returns to the shelf. The quiet theme under the technology is continuity. The same laws that let a lab cool atoms to near absolute zero also describe how a neutron star's superfluid core stores angular momentum. The same relativity that bends light around a galaxy sets timing corrections for satellite navigation. The same quantum rules behind lasers and atomic clocks enable interferometers to hear motions smaller than a proton's width. Future tools will likely extend this pattern. Advances in materials, computation, and control will bring extreme regimes into reach without changing the basic rules that made earlier instruments work. From this vantage, the universe is not a fixed picture, but a system that can be sampled in many ways. Each new method, timing, imaging, polarization, spectra, particles, waves, adds a dimension to the data. Cross-correlating those dimensions often yields more than anyone can alone. A kilonova's light curve tied to a chirp's mass estimate reveals how heavy elements form. A black hole's shadow size compared with stellar orbits fixes its mass and spin more tightly. A lensing map combined with galaxy clustering tests both dark matter and gravity at once. With better tools and broader baselines, the horizon of possible measurements widens. Errors shrink. Degeneracies lift. Models that once fit equally well begin to separate. Some ideas fall away, others survive and demand more detail. The cycle repeats. Build, measure, compare, refine. The pace is not uniform, and surprises arrive on their own schedule, but the direction holds. More of the sky becomes known in specific, quantitative ways. More of the extreme becomes accessible without leaving theory behind. And step by careful step, the picture of matter, energy, space, and time gains resolution, not as decoration, but as a guide for what to build next and where to listen more closely. The story of the universe is still unfolding, and curiosity is the tool that moves it forward. The objects and ideas we have followed, gravastars, neutron stars, dark matter, dark energy, show how far careful measurement and clear thinking can go. Each new detector, each better survey adds another page. We build instruments, compare predictions with data, and revise when results demand it. This cycle is simple and patient. It turns faint signals into knowledge and turns big claims into tests that anyone can repeat. One day, we may pull out a faint pattern in gravitational wave data that reveals a surface where a horizon should be. We may catch the particle behind dark matter in a quiet underground lab or a clever tabletop experiment. We may combine general relativity and quantum theory into a single framework that works from atoms to galaxies. Or we may find something that does not fit any plan we have drawn. That is not a dead end. It is the start of the next step, the moment when a puzzle becomes a program of work. The link between the cosmos and us is not abstract. The atoms in our bodies were made in stars and in the explosions that ended their lives. The calcium in our bones, the iron in our blood, the iodine our cells need, these came from nuclear reactions in places far older than Earth. the same gravity that bends light around a black hole keeps our feet on the ground. The same quantum rules that shape dense matter inside a neutron star also run the electronics in our devices. This is a single set of laws acting on different scales. Science keeps the language plain even when the objects are extreme. Time runs slow in strong gravity because clocks follow space-time, not because time breaks. Hawking radiation is a way fields behave near a horizon, not a special new kind of light. Dark matter is mass that does not glow, mapped by its pull on stars and light, not a myth. Dark energy is an effect that looks like a steady push on space, measured through supernova distances and the pattern of galaxies. Each idea stays tied to what we can measure, so that anyone can check it with more precise tools. The boundary between known and unknown moves with every decade. The horizon once sat at the edge of the map. It then moved to the orbits of the planets, then to the shape of the Milky Way, then to the deep field filled with galaxies, and now to the early light of the cosmic microwave background. With each shift, our picture of what we are changes. We learn that certainty is small and local, while the room for discovery is large. This is not discouraging. It is a reason to keep measuring because there is always something new to weigh, time or image. Even the hardest questions turn concrete when framed by tests. What is time? We check by comparing clocks in airplanes, on mountains, and in satellites. What is space? We watch light bend, measure parallax, and time signals. What is matter at the highest density? We time pulsars, track mergers, and read the cooling of compact stars. What is the fate of the universe? We map expansion across billions of light years and watch how structures grow. The questions sound big, but the work is a chain of small, careful steps. The universe does not promise comfort. Stars end, planets can be lost, galaxies collide and thin, yet the same rules that allow collapse also allow growth. Gas cools and forms new stars. Heavy elements seed new worlds. Black hole feeding can shut down star formation, and later quiet periods allow it to start again. The rhythm is change, not stillness. We are part of that rhythm. We are born, we learn, we pass on what we find. Knowledge outlives any one of us because it is written in methods and shared records, not only in memory. So the unknown is not a wall, it is a field to map. When data do not match, we check our instruments, share results, and look again. When an idea survives many tests, we lean on it to build the next one. When an idea fails, we learn where its limits lie and gain a guide to better models. This is how fire became chemistry, how lenses became telescopes, how clocks became navigation, how faint signals in coils and crystals became a record of space-time passing through matter. Think about light leaving a distant star. It travels for millions of years before reaching your eyes. That light carries a record of conditions long before people existed. It is not a message to us, but it is information we can read if we build the right tools. The same is true for gravitational waves, for neutrinos, for the polarization of the microwave background. The universe has been sending these signals since its earliest times. Only recently have we learned how to listen. Curiosity feels necessary because it connects us to that long story. It is not a luxury. It is how a species living on a small world learns to plan, adapt, and care about more than what is at hand. The same drive that lit fires and crossed oceans now builds interferometers, cryogenic sensors, and sky maps. The same patience that tracked planets now times pulses to microseconds and stitches radio dishes into Earth-sized instruments. In each case, method turns wonder into understanding without draining the wonder away. Our tools will grow sharper. A new detector will hear quieter waves. A new survey will map fainter galaxies. A new analysis will tease out a pattern we missed. Some results will confirm what we expect. Some will not. Both outcomes matter. Confirmation lets us use a rule with more confidence. Surprise points to places where our picture is too simple. Either way, we move. The map gains detail. The models shed unneeded parts and keep what works. The night sky is not a void. It is a record, a laboratory, and a set of ongoing processes that include us. We do not stand outside it. We live inside it and use its rules to build, to measure, and to explain. When you look up, you are not only seeing stars, but also the long chain of work that taught us what those stars are. You are seeing the next measurements waiting to be made, and the next ideas waiting to be tested. Keep the questions simple, keep the methods clean, and keep the links to data strong. That is enough to carry us forward. The rest will take time, and that is fine. The universe has plenty. As our instruments quiet and the last graphs for the night save to disk, the sky keeps shining with the same gentle steadiness. The signals are there, crossing the dark, waiting for the next clear run. And in that soft glow, the noise settles. The clocks drift in step, and the story continues fading, for now, to silence.